to the next day of SLE and the first session of the day. Thank you very much for showing up. I hope that you have enjoyed the banquet yesterday. My name is Vadim. I will be chairing the session, and we have 3 presentations planned ahead of you. Remember that we are streaming, so when you are asking questions, there will be a microphone in the middle of the room, so queue for that and ask your questions there instead of shouting. If you cannot move, then I don't know, give me a signal and I'll go to you with a microphone. All right, the first speaker is Ciprian Teodorov, and he will talk about temporal breakpoints for multiverse debugging. Floor is yours.
Thank you, Vadim. So, yeah, I guess I'll get to the next slide to speak about the motivation. So, in our context, we are thinking a lot about formal specification. Is the formal specification aligned with the model with the user? And knowing that these formal specifications are wildly non-deterministic, and basically we want something that in the early design phases aids the user the designer to interact with the partial specification in order to increase confidence either in the specification itself or in the properties that it needs to verify. And in the later design phases, if a property is violated, we'll like to have some interactive debugging to be able to do some differential diagnosis. On the other side, we have concurrent programming, and the idea is where do we get this set of behavior, this non-determinism? The problem is simple. If we have schedule-sensitive bugs, we'll have to somehow use the scheduler during to remove the scheduler during the debugger, or to generalize it in order to understand where that bugs come from, and that brings in non-determinism. But then, if we are doing that, linear breakpoint in classical interactive debugging becomes a graph reachability problem. So basically, it gets this algorithm from the formal specification side. And that was proposed as a multiverse debugger in 2019 at ECAP. But then this reachability analysis, if we have huge problems, we'll have a scalability problem. So in order to manage the scalability, we'll need to somehow do abstraction, either under approximations or over approximations, which increase even more the non-determinism and brings us closer from the programming world to the formal specification world. So in 2022, we proposed to reductions in models that brings again this under approximation ideas from the formal side towards this towards the interactive debugger. And since we are now speaking about sets of behavior instead of one linear behavior, we know from the formal methods side that temporal logic allows reasoning on sets of behavior. So the idea is how can we get this temporal logic to interactive debugging that now has to reason about sets of behavior. So our purpose is to leverage this interactive debugging in order to ease the life of formal specification engineers. I have some questions for you to ponder during my talk. Does your favorite debugger support temporal logic breakpoints? Does your favorite modeling tool have a debugger? If it does the debugger support these temporal logic breakpoints? If not, start using a better modeling tool. And I think this is maybe more like a call for the community to start thinking about these problems and start helping ourselves and our colleagues that are in the industry. And by the way, there is one tool that I know of that is doing this. It's Simulink. In their temporal assessment tool, they have this signal temporal logic that it's somehow implemented there, and apparently it's used successfully. So with this temporal logic idea, we'll have to reclassify a bit our breakpoints. So we have identified 4 types of breakpoints. We have configuration breakpoints. Basically, in this case, it suffices to look at each configuration during a run, the memory configuration of our system, in order to understand if some predicates are true or false. We have step-based breakpoints. which are evaluated on 2 link configurations by an action. So in that case, we have like memory breakpoints where we can break if a variable change. We have difference breakpoints, the rising age of a Boolean variable, the falling age of the variable, or activation breakpoints, basically the function X got activated or the action is triggered. And we'll have history-based breakpoints, where the breakpoint conditions evaluated by integrating some variable over the history of the execution and then checking that variable for a value. So there maybe we have a breakpoint that will say, let's take the sum of A, and if that sum becomes greater than 2, then break. Or I want to break on the third occurrence of the function f. So do you see this counter getting there and getting incremented as we progress during the execution? And the last breakpoint, and maybe the most extreme, it's coming from temporal logic, where we, instead of having this look in the past, as we had with the history-based breakpoint, we start looking to the future in order to start to understand if there are some infinite behavior that will prevent useful work. And basically that will help us isolate some cyclic behavior or something that we want to happen doesn't occur. And basically we can say something like A equal to 5 is inevitable. So that will mean that if ever we find a behavior that where a cyclic behavior where A is not equal to 5, then we have a problem, because if the system, the scheduler will get us in that loop, we might get stuck, become stuck there forever. Another, it's eventually forever B becomes false. So basically at some point in the future, B becomes false, for instance here, and then it needs to stay false forever. But here we see we have this loop where B becomes true again. So that invariant is not true. So let's take a step back and think a bit of how can we build these tools that survive and that we can reuse them. So there are a bunch of approaches, and I show you here 3 of them. The first one is like take a language, like MATLAB Simulink, as I was saying earlier. It supports this temporal assessment, and let's do transformation towards that language, and then use that debugger. But then we have this impedance mismatch in between our initial formalism and the formalism of our debugger. Another approach, which is common in this community, is to have some meta-language tooling that will help us generate the tools for testing, for coverage, for debugging. And but we are in the last, this old school category, let's say, which is more oriented on API and like say, okay, we have this black box hypothesis. I don't want to care about either the meta-modeling language or the way the people are implementing their semantics, as long as I can write some glue code that will expose some API that's somehow common, confluent in between a set of tools. And that enables us to explore this space from a tool perspective with exploring basically families of tools. And today, the family that we're exploring is debugging, and more specifically, multiverse debugging. So in multiverse debugging, we have a bunch of stakeholders that will provide us with a specification, and they want to ask some questions about the specifications, and in our case, those will be multiverse breakpoints that are breakpoints on these sets of behaviors. And our stakeholders will interact with the semantics of the debugger through debug actions, and they will observe projections of the debug configuration that will tell them, yeah, you are here in the multiverse, and you can go there, and that way. So in order to make this modular, we'll have to have an API here that it's implemented by our specification language that's designed by any subject language provider. And the other side, in terms of the breakpoint language, if we want to open the box and allow different logics to be used for the breakpoint language, we'll have a similar API. However, we should note that the breakpoint language, it's dependent on the execution of the specification language, on the semantics of the specification language. So that's a small point. So what is this interface? It's rather intuitive. We have some generic types. The configuration type is like the memory dump of the semantics. And then we have a set of initial states, the actions that we can execute from one state, and an execution function that basically, given an action and a memory state, it will give us a set of target configurations. And this is an approach similar to the temporal logic of actions of Lamport and omnisemantics that presented this year at Toplas. And in order to be able to ask questions over the semantics, we'll have this evaluation function that will evaluate a given expression over a computational step, and it will give us some value. To do the under approximation, we had proposed to use a reduction function that will map any configuration towards an abstract value, alpha, and a bunch of projections that will show the user the state of the debugger and the actions that he can take. So from this perspective, what is a multiverse debugger? Basically, it's this dependent semantics. We need a subject language semantics here that has a step action. So basically, if I'm somewhere in the execution, I might want to step to the configuration 4 or to the configuration 5. I have to be able to jump back in the past to allow this time-traveling semantics like in omniscient debugging. We have the need to have a select configuration because from one configuration, while running an action, if our language is non-deterministic, we might get multiple target configurations. So we have the select action, and finally the run to breakpoint action, which basically will have to do this reachability-like analysis or over the state space. So in this approach, the multiverse debugging semantic is independent from the subject language, and it's built through composition of these smaller operators, the blue operators and the algorithms and everything. So the scalability comes from this reduction part, and we have connected it in the past to the AnimUML semantics. So now today, the story becomes a bit integrated because we have to replace this run to breakpoint implementation, which was limited for configuration-based breakpoints, and to get to these temporal breakpoints. And how do we do that? It's a lot similar to model checking, with the big difference that we'll have to replace the initial state of the original semantic from which typically we start the model checking, and then we'll have, so basically in ongoing debugging semantics, we'll start somewhere, we'll do some exploration, maybe get to 5, we'll go back, we'll go to 3, and then we get to 7. And at this point, we want to start the run to breakpoint operation, and basically we feed it in a finder function that will replace the initial configurations of the subject language. Then we get the breakpoint, which will be represented for simplicity as an automata here. We get the breakpoint with its semantics, and we do a synchronous composition in between the subject language and the breakpoint language semantics. But basically, this is a lazy synchronous composition, and that basically helps us to get the breakpoint to filter the execution and in order to focus on the parts that we're interested in. And then, as is typical for model checking, the subject language will consider that the subject language semantics has all its states as an accepting state, and then basically the intersection will consider only the states where the breakpoint automata has accepting states. Okay, so we compute this, lazily compute this, we have this specification that will allow us to compute at runtime the synchronization. And then we have to do like a lowering path that will transform our rich semantics into like a more graph-like structure that's again done lazily, and an emptiness checker algorithm, which is standard algorithm from the literature. So basically, in our example, we'll start from 7 and we'll start exploring. We'll get to 8b, and we can stop because we found an accepting state. When we have found an accepting state, what do we have to do? We have to compute the witness trace, as is typical again in the model checking community, and patch our history from the 7 that we had, where we have started, with the witness trace that we have found. And then show that to the basically the state of the omniscient debugger semantic changes. So the AnimML tool presented in 2020 at Models basically allows us to do some state chart modeling with class modeling and everything. And the idea since the beginning was to allow us to do execution of partial models. So last year we have implemented the reduced multiverse debugging inside. So we have this branching history that allows us to walk in time on different universes, and to write these reduction functions and everything. And today we have integrated again AnimML with this more generic approach where the breakpoint language, where the breakpoint condition becomes a language itself, actually. And basically we have this debugger core, the finder function that we have seen, and the dependent semantics that will have to fill in somehow. So we took the previous implementation of this AnimML subject language. We had to re-implement the evaluate step function because it wasn't there, because previously we were supporting only conditional breakpoint on the configuration. And then we implemented a bunch of different languages with different semantics for the breakpoint language. So we have a simple regular expression language. We have a breakpoint language which uses AnimML state chart themselves as a breakpoint language. So we have the specification as an AnimML state chart, and then we can specify these small state charts that are dependent on the subject state chart. And we can do history-based breakpoints with them, and step-based breakpoints, and configuration breakpoints. For the liveness breakpoints, we have to use a different emptiness checker because our automata that we need to use for that becomes like a Bushy automata, and in order to find these cycles in the execution. So basically we were able to reuse some tool that we have developed some years ago that are transforming LTL to state chart-based Bushy automata, and again, reuse the semantics that we have enriched here of AnimML in order to be able to do that. So, so these are temporal breakpoints which increase the conditional breakpoint expressivity. We propose formal methods, taxonomy inspired by the literature, where we can speak about the state, the execution step. We have a look in the past through the safety properties, in the future through the liveness properties. Basically, this approach enhances the genericity of the language agnostic multiverse debugging that we already proposed last year. Everything is formalized in Lean. It was illustrated to the integration of in the AnimML environment, and you can have the code here. We have 3 different breakpoint languages, as I just told you. And basically, we had a paper at Modeva 2023 where we tried to use it to debug Paxos and have this interactive approach to building a Paxo consensus algorithm. So tomorrow it will be relatively easy, we believe, to do some user study that will try to understand what are the needs, what are the opportunities of temporal debugging in the context of complex specification. And it will be really nice to go from the command line interface that we have today as an implementation to a nice graphical user interface with some real user experience help magic. Yeah, not so easy. It will be to find a trade-off in between the intuitiveness of the logic that we are using for expressing breakpoints and its expressive power, and that's typical in the formal methods community, and it has a huge history, and we are oscillating in between all these things, and yeah, that should be solved somehow one day, maybe. We should be hopeful. And we see some difficulties that might arise if we are having heterogeneous specs where you have these multiple languages. Then the composition should work, the approach that we're presenting should work, but there might be some details that need to be solved if we're having some, let's say, mixed signal or abstractions that are mixed at different levels in our specifications. So thank you very much. I forgot to mention at the beginning, this work was done mainly by Matthias Pasquier and in collaboration with between ENSTA Bretagne, ESEO Angers, and Lucio. And yeah, what do you think? I have a bunch of questions for you also. So thank you very much.
We have time for questions, so please come up here.
So thank you very much for your interesting presentation and work. I wonder whether, to which extent the breakpoint part of your system requires the jump operation that's part of the interface, because that seems quite a tough ask on language implementations.
The jump operation is just an operation that it's useful for multiverse debugging. But actually, the run to breakpoint doesn't require it. The four operations that I'm presenting here are somehow independent. But at the same time, that's at the multiverse debugging semantic level. However, when we're implementing a reachability like query over the partial state space, in this case, starting from the node 5 there, in order to get to everywhere, yeah, then you have to have some storage requirements, and basically you get typical issues that you have in a model checking context. That's why we have thought about under approximations and yeah. But the jump, it's not required. If we don't store the history, we are not able to go back in the past, and that will be fine. It will be like more like a typical debugger, and we'll still can implement this run to breakpoint.
Okay, that's very clear. Have you considered any other case studies, or are you aware of languages that you would be able to apply your implementation to directly?
Actually, the first prototypical implementation that we did was on TLA Plus in like 2016 or something, where we had some of these ideas already working a bit. This is a lot nicer presentation than our prototypical implementation that we did back then. And I think now the formal specification community starts to understand a bit the interest behind debugging. And TLA Plus has a Visual Studio Code extension that implements more like software debugging. It doesn't get this sophisticated, but it's a good step towards that. I think VDM community has something around it. B method has something around it. And on the software side, the initial paper was motivated by the debugging in actor formalism. in like I don't know what was the name of the actor formalism studied, but yeah, I don't know the real implementation on the software side that's used. Besides, of course, MATLAB Simulink with their temporal assessment.
Still have time for questions? All right, I'll go with one of mine. So in your case, you see basically a breakpoint as an automaton.
At the end of the day, it will become that, yeah.
Yes.
It's the semantic of the breakpoint will be the semantic of the language, which we see it from an operational perspective as a state transition system. So an automata.
Yeah, but
it's not really
later, in order to merge it with the configuration automata and so forth, you really need the automata power, right?
Yeah.
So automata have a very nice hierarchy. So where do we need to be in that hierarchy, and what are we missing by staying at non-deterministic finite automata, which is, as I understood, if I understood correctly, the current state? But you did mention that at some point, when you go further, you need a Brugge automata.
Yeah. So basically, non-deterministic finite automata from the actually, I think on that side we might get to maybe get to push down automata and a lot more expressive logics on the breakpoint side, but will probably be limited at this look on the past. In order to be able to look and identify infinite behaviors that don't that preclude useful work, then we have to go to these cycle detection techniques and fixed point computations, where we get to these more sophisticated approaches like Bucci automata, Rabin automata, mu calculus, where we have this power of computing complex fixed point over the state space of the subject of interest, you know. So it will be interesting to see where can we get, and I think this maybe one of the things where I'm rather proud of this approach that we have here is that it puts the question on the table, and it somehow bridges the gap in between these model checking guys that are very sophisticated and mathematically friendly, and like programming community where, yeah, we have semantics and we can implement them. We can implement this interface. We did it for BPMN, for UML, we did it for TLA+, we did it for a bunch of SDL, for a bunch of formalisms. So the semantics are there, they are implemented, and now let's bridge the gap and like have simple tools like a debugger, allow us to reason with temporal logic, and this way maybe the designers will get some feedback before verification part, where you have this huge temporal logic formula, this huge specification, it doesn't work, and you start scratching your head, and you are basically, yeah.
Okay, thank you very much. Let's thank the speaker once again. And can the second